All right, so in this section, we're going to start to look at non-idealities and small size effects that have to do with real MOSFETs compared to the ideal model we've been dealing with. So a few of these effects will modify the magnitudes of currents. A few will change the effective input impedance to the device, and a few will change the threshold voltages. So we'll take each of these in turn. Okay, so the first effect we're going to consider is called subthreshold conduction. And we've talked about the channel as being in either an on or an off state, sort of implicitly in our discussions so far. But what we have to realize is that we're dealing with a semiconductor here, which no matter what voltages or band bendings we apply to it, is always going to have some amount of conductivity in the channel. And this showed up also in our last discussion where we had the parasitic resistance through the channel as one of our equivalent circuit elements. So what we want to think about here is a case where we've applied some voltage, or maybe we're even in the no voltage applied state, but the Fermi level is closer to the conduction band in this. So we have a P-body, N-channel enhancement mode MOSFET as our model here. We're closer to the conduction band than we are to the valence band, but we're still below threshold. So the surface potential is less than threshold. However, we do have some slight accumulation of carriers here. So this is going to mean that there's some conductivity in the channel. So if we draw out our ideal V source drain versus I drain, we would predict this curve intersecting at V threshold. And in reality, we're going to see the onset of current, which is exponentially dependent on the source drain voltage below threshold. So why does this happen? We can look now at a band diagram which is orthogonal to this one. So this is the band diagram when we're looking between the, looking in the depth direction of the MOSFET. So now let's look laterally through the channel. So we have our source and drain here, oxide and gate metal here. And if we take a cut along this line here and make a band diagram, what we'll see is that it should look something like this. So our V source drain appears here in the difference between these two portions. And we're going to consider a case where the threshold voltage would be here. So our threshold voltage is 2 phi p. So now as we start to apply the gate voltage, we're going to start moving this middle section up and down, and really we're going to start pushing it down and down and down with increasing V gate. So we're going to lower the energy for the electrons on this band diagram by applying a plus voltage to the gate. So now the channel here has not gone into inversion because we need to apply enough voltage such that it actually crosses this line here. So this would be the condition V gate equals V threshold. But it is possible for electrons to be thermally excited up and over this barrier at these various subthreshold voltages. And once they can get up to this kinetic energy here, they can make it across and down into our drain, giving us this subthreshold conduction here. So we should expect then, because this is a process of overcoming a barrier, that there's an exponential temperature dependence associated with it. So we can wrap up without deriving the whole physics and mathematics of this phenomenon, but we can look at the subthreshold current as being proportional to a term which has to do with the gate source voltage over kBT times something that looks almost similar to an ideal diode expression, except there's a minus sign here. And minus EV drain source. So what this says is, as the gate voltage is increased, this problem will become bigger. And you can see that because this barrier will be lowered, and it's hence this term. And then this part here says that the driving force to go from here to here, which would actually induce some slope to these bands, will be driven by the amount of voltage between the source and drain also. So this subthreshold conduction essentially makes your quote-unquote off state less off and reduces the contrast between on and off. We'll also see that very similar effects happen as you start scaling the channel length. So we motivated, when we talked about cutoff frequency, that the channel length shrinking will actually allow us to run our MOSFETs faster and get greater bandwidth. But one of the consequences of this is many of the physical effects will manifest as essentially increased subthreshold conduction, as well as changes in the threshold voltage itself. So in this little section here, we're going to explore some of the other consequences that happen because of the pinch-off effect in the channel of a MOSFET. So two things happen. The voltage distribution between the source and drain changes because of the introduction of a depletion width. And then the second is that the effective channel length changes. So let's come over here to this diagram. So in pinch-off, what's happened is we've extended the depletion width around the drain, especially because we've applied some source to drain voltage. And remember, we're assuming this is grounded. So this has brought this depletion width out. But it doesn't just move in the vertical direction, it also has to move horizontally. And so in effect, the depletion widths around the drain and the depletion width that's emanating down from the gate superimpose on each other, and the total voltage, being a scalar quantity, is what determines the depletion width. And really this becomes a three-dimensional problem. So in this two-dimensional cross-section, the consequence is that the inversion charge will go to 0 at a certain point that's partway along the channel. So this is the pinch-off. And that means that part of the current flowing through the channel has to pass through a depletion width, which has very high resistance compared to the very low resistance where there's a total inversion charge. So that results in an additional apportioning of the total voltage applied here, and we've drawn this here in blue. So over the length which is not pinched off, we drop a certain amount of voltage, which is here, the drain source voltage minus the saturation drain source voltage. And then we add this additional resistance, which means we're going to have to add a whole bunch of extra voltage in order to get the same amount of current to flow from source to drain. So that's represented here. Now also, because the drain's band diagram can kind of be thought of as being given by this equipotential line. So I've superimposed the voltages from the gate and the drain, and I've drawn a line of equal potential, which is defined by the depletion widths emanating from all of them. So this would actually be a reasonable picture of the band diagram itself. So all our electron has to do is make it to this point right here, and then it falls into the drain automatically because it's swept through the depletion width. The net effect is that the effective channel length becomes smaller and becomes dependent on the source drain voltage as this depletion width modulates the position at which this pinch-off happens. So this whole big nasty equation gives us the channel length modulation, and we can write that L prime equals L minus delta L here. Now the drain source, the delta drain source here is this little extra bit of voltage here, and it is essentially looking at just the straight subtraction of L and L prime here. So what does this do in terms of the performance or behavior of the device? Well, let's look to our trusty IV curve, and the effect is that it gives you a slope in the saturation region, where before it would be flat, and thus 1 over R is a slope, which means that if the slope is 0, the effective impedance would be infinite. And in the real case, our slope is greater than 0, and so our resistance must go down from infinity to some reasonably large but non-ideal limit. So this means that one of the functions of our MOSFET or transistor in which we could use it to isolate parts of the circuit from each other has been degraded by this effect. So in addition to the non-zero slope, what we see here is that for the ideal MOSFET in the saturation region, the current is proportional to 1 over L. So if we make the effective length smaller and we change this L to an L prime, making that a smaller number, what that means is our current will also go up. So I'll draw what would be the ideal curve, and what we've done is shifted up the apparent point where the saturation would happen, but then also introduce this slope. So whereas before we saw that the presence of the saturation itself is a consequence of pinching off the channel, additionally, if we look beyond that point where it first pinches off right at the edge of the drain, there's also some modifications to the current voltage curves that occur. So again, we move between the ideal and non-ideal cases because of this pinch-off and channel length modulation, which happens inside the MOSFET. So next, let's look at the changes in the physics of transport in the channel. So we have to look back at our definition of mobility. And we have to remember that the mobility is the sum of the mobilities from each different mechanism. So I'm just writing, mechanism A, mechanism B, and mechanism C, where each of these mechanisms is a way of scattering the carriers. So typically we have phonons, impurities, ionized, dopants, and now we're going to add a new one, which is roughness, and even another one which kind of has to do with ionized impurities, but scattering from charges at the interface. So if our electrons were just traveling through a bulk semiconductor, we only have to worry about these three. Now, however, if the mean free path of the electrons, which, remember, the mean free path is the average distance between collisions or scattering events of the electron, and this is going to be equal to the thermal velocity times the scattering time tau. If this mean free path becomes larger than the effective confinement distance of the carriers, then we're going to start to have issues with carriers scattering off the interface. So I'm talking about here an effective distance here, t, and if the mean free path L is bigger. So I'm drawing here the oxide to semiconductor interface, including the band bending, for again our enhancement mode p-body MOSFET. So we have to look then at this interface. Here's our oxide, and we're going to imagine that this interface is not completely smooth. It probably has some roughness, and this will act to scatter carriers. Also, if we have interface charges, and these can be plus or minus, remember that each of these will interact with the electrons in the channel through a Coulomb attraction or repulsion field, again, adding additional scattering. And lastly, this sort of confinement distance here, T, is going to change depending on what voltage we apply. So for very high voltages, we'll have our bands bent steeper and steeper, and thus this thickness will be sort of smushing the electron inversion channel closer and closer to this oxide, enhancing this, these effects of the roughness and Coulomb scattering. So we should expect then some dependence of the effective mobility in the channel related to the gate voltage. And indeed, it turns out that the mobility as measured through measurements of the transconductance of MOSFETs will show a minus 1/3 power law dependence e to the 1/3. And we're looking here on a log scale. So log mobility log E field. And remember that our E field is going to be essentially the so V gate minus the voltage dropped in the oxide divided by the depletion width, which again has its own scaling of square root of V gate. So there's a complicated mathematical form which leads to the empirical minus 1/3 law here. Other things can happen which bring us out of the mobility regime. Now this E field here is the E field along the Z direction, which has to do with controlling the depletion width and the inversion charge in the channel. Now, we've also got another orthogonal E field going on between the source and the drain. And if we apply a high enough voltage between these two, we can actually get a large enough lateral E field to speed up the electrons to their saturation velocity. So I'm labeling this one EX, which is the horizontal or in-channel E field, and then the EZ is the vertical E field, which is controlling the charge in the channel. So again, we go back to our earlier discussions of semiconductor physics, and we remember that, this is the velocity of the electrons as a function of E field looks something like this. So this is the constant mobility range where we have a constant slope, and then this is our saturation velocity. So in the derivation of the IV curves for the ideal MOSFET, we've assumed that the mobility is constant, but the mobility, the differential mobility essentially goes to 0 out here in the saturation velocity regime. And this E field that we're talking about is our EX, the lateral one causing lateral transport. So let's look next at what happens because of this effect. So we can fairly easily understand qualitatively what happens to the MOSFET IV curves as a function of this velocity saturation effect. So here again is our diagram showing the velocity of carriers as a function of the applied E field. So in the low field range here, where we have a constant mobility, we have this expression governing our transport. And this leads us to essentially the expression of Ohm's law here, where we have J equals sigma times E. And thus this part here is our conductivity. So Ohm's law applies, and we get current, which is proportional to the E field. And in the case we're talking about here, we're talking about our source, drain, separated by a distance L, and we're applying between the drain and source, which results in this EX, where EX is approximately V drain source divided by L. So if we reach a high enough E field because we've brought the channel length small enough by physically shrinking our MOSFETs, we're going to be out here in this velocity saturation region pretty quickly for moderate source drain voltages applied over short distances, which today are measured in perhaps tens of nanometers distance. What this means is that Ohm's law no longer applies, and we are getting the carriers to go at a slower velocity than they would have otherwise. That means that the total current being pushed is going to be decreased for a given voltage. So we can come back to our IV curve for our MOSFET. So if in the ideal case it would be doing something like this, because of this velocity saturation, we would get a lot less current for any given voltage. The initial slope at very small voltages is going to be the same because we're operating in this region, but as soon as we roll over into the saturation velocity regime, we'll significantly drop the current. So also, in today's MOSFETs, this length is becoming so small that the mean free path for the carriers might actually be much, 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 much bigger than the channel length. And then in this case, we'll actually get ballistic transport, where no scattering whatsoever occurs on the way between the source and the drain. So in essence, the ballistic transport means almost zero resistance. So we'll tend to actually shift the mobility higher and higher here. And that would mean that the effect of ballistic transport would be to raise the current for any given voltage. So these two effects are definitely in play in today's modern MOSFETs, and especially the ballistic transport, and in fact moving into models of quantum transport because the distances are getting so small is necessary these days in designing modern and advanced transistors.